This is problem 641. In this problem we're looking at a chip on a circuit board, and it refers back to problem 639. You see down at the bottom here, this is taken from problem 639, where you can see you have airflow going over the chip with the prescribed Nusselt correlation. Notice that Nusselt is a function of x, and x is the distance from the beginning of the circuit board out to the position L of 120 millimeters. In this problem here, we're looking at a maximum chip temperature of 85 degrees C, and also the incoming air is fixed at 25 degrees C, but the velocity is varying. And so what we're trying to do here is determine what's the maximum amount of power the chip can produce for a given velocity distribution between 1 and 25 meters per second, and an incoming fluid temperature of 25 degrees C. And the second thing we're going to do then is also include radiation to the problem. So let's look first at part A. In part A, we're given that the maximum temperature is 85 degrees C, and that the fluid temperature is 25 degrees C, and that the velocity is going to vary between 1 and 25 meters per second. We're also provided with a distance of 120 millimeters, or 0.120 meters, between the middle of the chip and the start of the circuit board. And we're also shown that the chip has a width of 4 millimeters. Also, the chip is square. We're also provided with the Nusselt correlation that's shown here in the figure. So given these things, we want to find what is the maximum power you can get as a function of velocity. So let's do our energy balance here. dEc v dt equal to E dot in minus E dot out plus E dot gen. We'll draw our control volume around the chip. We know that there's convection leaving the chip. We know that we have our power, we'll call P max, is inside the chip. So this is under steady state conditions, and there's no energy flowing into the control volume. We do have convection leaving the control volume, and we have our power as heat generation. So it's a simple energy balance here. We just simply get that your power is equal to the convection heat transfer, which of course is HA. In our case here, the chip temperature is at T max, and the fluid temperature is T infinity. And we know the area is little l squared because it's a square chip. So the only thing really that remains is we have to figure out what the heat transfer coefficient is. We're provided with the Nusselt correlation, so that makes life much easier for us. Nusselt correlation states that Nusselt at some position x will be hx over kf will equal then to 0.04 Reynolds at that position x, 0.85 Reynolds to the 1/3. So this is a local heat transfer correlation. And if we look at the diagram, we can see that the chip has a very small size of 4 millimeters compared to its distance from the start of the circuit board, which is 120 millimeters. Therefore, we can use this local Nusselt correlation. So we replace our x's here with capital L's, and this will allow us then to determine what the transfer coefficient is. So we move the k sub f and the L over to the right side, and we get h is equal to 0.04 k sub f over L times the Reynolds number evaluated at L, which will be V times L over nu, to 0.85 power Reynolds to the 1/3. So this connects then our heat transfer coefficient to the speed of the flow. You can say that h is a function of speed then. It's going to be 0.04 k sub f. You can see that we have an L to the 0.85 power in the numerator and an L to the 1 power in the denominator. So this becomes L to the 0.15 in the denominator times nu to the 0.85 in the denominator. We'll put our Reynolds to 1/3 in the numerator. All of this times the speed to the 0.85 power. Putting it back into our relation for power, we get the power, the maximum power at speed v is going to equal then to 0.04 case of F, times parental to the 1/3 times little L squared times T max minus T infinity, divided by L to the 0.15, nu to the 0.85. All of this stuff inside is constant. We're going to vary the flow speed. So the second part of the problem looks at how would you integrate radiation into this. So for part B, we're going to have radiation leaving this out to some surroundings temperature, which we can easily add to our energy balance here. So for B, we're given that an emissivity is provided of 0.8 and surroundings temperature 25 degrees C. So again, we want to find V max as a function of flow speed V. The only thing different from part A is that the energy balance changes. So now for E dot out is equal to Q convection plus Q radiation. And Q convection stays the same as in part A. So Q radiation, we have to figure out what that is. And it's pretty simple. We can use our Stefan-Boltzmann law. It's A epsilon sigma T to the 4th, in our case it's T max to the 4th, minus T surroundings to the 4th. And furthermore, our area here is going to be little L squared. So we're just adding on an extra term then to our equation for P max. So what we can do then is we can grab our original equation and then simply add on to the end of it L squared epsilon sigma T max to the 4th minus T surroundings to the 4th. And you have to be careful because the temperatures in the second part of the problem, since you have radiation, are required to be in Kelvin. So the only thing left we need to do then is we need to figure out then our thermal properties. We need to figure out what values are for case of F, for Prandtl, and for nu. So we need to look these up in a table for air. But we know that these three thermal properties depend on the temperature at which we're evaluating them. So we'll use the film temperature, T sub F, which is 1/2 T max plus T infinity, which is 1/2 times 55 degrees C plus 25 degrees C, and that gets us then 55 degrees C, which is equal to 328 Kelvin, which we'll say is roughly equal to 325 Kelvin for our purposes here. So if we look at the air properties table, we don't have anything right at 325 Kelvin. We do have 300 and 350. So what we can do then is look at value of nu. It's going to be halfway between these two numbers here. K is going to be halfway between those two numbers, and Prandtl will be halfway between these two numbers. So let's go ahead and put this into MATLAB then. So now we're in MATLAB, and we can open up a new script. In this script here, we'll call it ME3950, problem 6.41. And we always start by clearing the memory and clearing all the listed text on the window. And we'll close all open files. Now we can declare our constants. Our thermal conductivity is going to be half of 1263 plus 0.030. So listed as thermal conductivity, loss per meter Kelvin. Our kinematic viscosity is going to be half of 15.9 e to the minus 6 plus 20.92 e to the minus 6. Finally, our Prandtl number is 0.5 times 0.707 plus 0.700. Next, we can put in stuff that we know from the problem statement. We know that the position of the chip relative to the beginning of the circuit board is 120 millimeters. With a little L, is 0.004 meters. We know that the maximum temperature of the chip is 85. We know that the fluid temperature is 25. So for part A, we're going to plot the maximum chip power for varying flow speed. And so to do that, let's go ahead and define a coefficient of everything that was in the brackets from what I showed you earlier. And then we'll write our range of flow speeds. So we start at 1 meters per second. We'll vary it by 0.1 meters per second. And then we'll end up at 25. So we're going to have increments of 0.1 meters per second going from 1 meters per second up to 25. And in MATLAB, it's easy to work with this since we have a vector here, v. We do this dot and then the hat symbol to take every element of v and then raise it to the 0.85 power. So this will allow us then to obtain our chip power. So we're going to plot this. And we'll label the x-axis as the flow speed, meters per second, and the y-axis as chip maximum power, watts. So let's save this then. Problem 6.41, and we'll run it. And if you run it, here's what we get. You can see then that, of course, as the flow speed increases, the chip maximum power will increase as well. Starting with a value on the order of milliwatts up to about 200 milliwatts or so. Now for part B, we're going to add in the effect of radiation. So to do this, we're going to have a hold on. This will hold the plot on, and we're just going to fall on top of it. We're going to provide an emissivity of 0.8. We're going to provide a Diphon-Boltzmann constant of 5.67 times 10 to the minus 8. Watts per meter squared Kelvin to the fourth. And you know that the surroundings have a temperature of 25 degrees C. But we have to put everything in terms of Kelvin here. So we need to take our values then for Tmax and T-infinity and also update them. So Tmax is equal now to Tmax plus 273.15. And then T-infinity plus 273.15. Our equation for power is the same as before, except we're adding in a radiated term. So we're going to take that value from before and say L times epsilon times sigma T max to the fourth times T surroundings. We're going to make another plot. This one will make it red. We're also going to add in a legend to show the difference between the two lines. So we have one without radiation and one with radiation. So now we'll plot this, and you can see we have two lines now.